No. No, I told her that it'll separate like the strong kids from the weak kids, like you said. And she's like, don't worry about it, we're strong kids.
Okay, so let's do a recap of last time, where we left off. So we're getting into some pretty cool stuff now. So we investigated two circulation integrals, as we call it, like integrals over a closed loop, which we call it, you might call circulation integrals. The same two, we looked at the same two loops in two different vector fields. We looked at let's see. So I think we did what? We did a counterclockwise loop on this one. We'll call that C1, right? And then we did a clockwise loop on the triangle. Is that right? And we called that C2. And so what integrals did we evaluate? We evaluated the circulation. So if it's a closed loop, your path is a closed loop, you can put a circle there. And we call that a circulation integral. And so we did cyclus F1. And so we have C1. And so when we in this vector field F1 negative 2y, we did the closed loop, we did the integral around the closed loop C1, and we got, what did we get for that one? Remember? We got 0. And likewise, we did the circulation integral for the triangle, C2, and we got 0. By no means does that show that every circulation integral is 0, but we said that it was, okay? I said, just trust me. So because of something about this vector field, every closed loop, every integral over a closed loop path would give an integral of 0. But then on this one over here, we found that was not the case. So for F2, we did the same two paths. And I think, did we get pi or something, or what did we get? No, that was later. So around the, whatever it was, it's non-zero. And we did both of those. We did the triangle, we went around the triangle, and we ran around the circle, and we got non-zero. So we said, okay, there's something special about that vector field over there. What's special about that vector field? It's a gradient field, right? And so this is a gradient field where this is not. And so this characteristic of a gradient field that results in all integrals over a closed path being 0 was that a gradient field is conservative. So if it's work, if this is a force field and we're calculating the work, by the time you make it back to where you started, all energy is conserved, right? Energy is conserved. The energy that the work done by the vector field is equal and opposite to the work that the thing moving in it put back in. So whenever this object was going against, like this way, on this path right here, it's going against the forces. So now that object is actually doing work back on the field, where the work we calculate is negative. And so the sum total of the work is 0. So it's the conservation of energy, right? So that's why it's called a conservative vector field. And so then we focused on that conservative vector field. Oh yeah, so if it's not conservative, then when you make it around, so clearly this red loop integral would be what? Positive or negative? We go around looking at those vectors. What would you think? Going around one loop counterclockwise? Would you think that that's going to be positive or negative? Positive. So it's really strongly positive across the top. Do you see that? And then it's kind of like 0 here, and then negative around the bottom, and then 0 here. So that positive is going to dominate, right? So all the work that the vector field is doing is going to be more than the little bit of work that the object does back on the vector field here. So it's like positive, little 0, little negative, 0. So positive. So we don't have conservation of energy because the vector field is doing more on the object than the object puts back in, right? Does it make sense? Okay, so then we focused on the conservative vector field. And we said, let's look at this starting from point A to point B here. And we calculated the work from point A to point B. And what did we get for that? Negative 10.5. So this is the integral, and this is not a circulation integral, just but on this path. And we got negative 10.5, right? Why negative? And why not 0? I thought this was a conservative vector field, so the integral should be 0. Not closed loop, right? So it's not going to be 0 necessarily. It could be 0, but it's not necessarily 0 unless you close the loop, right? Okay, so from A to B, we got a work integral of negative 10.5. And then I said, all right, let's calculate then. I want to look at from B to A along this path. I said, okay, let's find the work to go from B to A along the straight line path. And after about 3 seconds, I said, I know the answer. Why can you know the answer? Because we're in a conservative vector field. What would the total work done to go from A to B and then back to A? It's going to be 0. It's a closed loop, right? It's a closed loop. So if we know from A to B was negative 10.5, then from B to A along this line would have to be positive 10.5 in order for the loop to be 0. I kind of did that fast. Hope that made sense. So this is C2. So now along C2, because of we know that every closed loop in a conservative vector field is going to have a 0 integral. We know that to get from there to there was negative 10.5. Therefore, it has to be positive 10.5 to get back. Does that make sense? Okay, and so then we looked at another path. So what if we went up straight vertically from B? So let's say we did this. So this is C3. So along C3 from B up to here, over to A, what should that integral be? 10.5 again, right? Because that's another closed loop. If I go around this arc and then up and over, that's a closed loop. Total work has to be 0. So if that part of it's negative 10.5, then the rest of it has to be positive 10.5. Does that make sense? And so really we said then so what is any amount of work done starting from B along any path to A. Positive 10.5. Because that, no matter what path I choose, that would close the loop that I started going from A to B. So this was the idea of what's called path independence. Just looking at no matter what path you take, starting at B back to A, you're always going to get the same amount of work. In this case, positive 10.5. Now, change points B and A, you're going to get a different amount of work. So this path independence is on the premise that your starting and ending point stay. They don't. As soon as you move them, you get a different amount of work. Okay. So this is the idea of path independence. That given any starting and ending point, any path of the vector, the line integral over any path will give you the same value of the line integral. Okay, so let's summarize that. Any questions on? So that's a recap from last time. Questions on that? So let's talk about conservative vector fields. So here's a bunch of statements that are all mathematically equivalent. Okay? If any one of them is true, then the rest are all true too. Given any one of these to be true, all the rest are necessarily true. And the first one is, so F is a conservative vector field. Okay, F is a conservative vector field. What are all the implications of that? All right, the first implication is F is a gradient field. If F is conservative, then it's a gradient field. And what does that mean? That means there's some potential function such that F is the gradient of little f, of your potential function. So what does that mean for the components of big F? The components of big F are what kinds of things? Partial derivatives. The partial derivatives of the little f potential function, right? Now, I'm using bolded F and F with an arrow over it interchangeably. Those mean exactly the same thing. My PowerPoint cannot put arrows over F's. An equation editor cannot make bold F's. And I'm using both. So, bold F and F with an arrow, just on your paper, make them all the same. Just use the arrow, right? Just do F with an arrow over it, wherever you see a bold F, okay? Next thing. Or here's a new thing. So there's a new thing. Do you remember back when we were doing partial derivatives, this thing called Chloros Theorem? Didn't talk about it extensively in class. You just had a couple homework problems on it. I think I put a note on Blackboard. And Chloros Theorem says this: the second partial of the partial with respect to x with respect to y is equal to the second partial with respect to y and then with respect to x. That if you took the second partial in terms of your first variable and then the other variable, you get the same things if you switch the order of taking those derivatives. So therefore, if our vector field is a gradient field, then really, what is P? P is partial with respect to, what is P? The partial with respect to x, and Q is the partial with respect to y, right? So if I took the partial of P with respect to y, meaning fxy, that ought to be equal to the partial of Q with respect to x, meaning fyx. Does that make sense? So now if I take my components and do these partial derivatives, so that these are like second partial derivatives, they should be equal. So P with respect to y should be equal to Q with respect to x. Okay, so let's check that. What did we have? We had negative 2y and negative 2x. So we're making a list here. You might not want to interrupt the list with this example, so this will be fast anyway. Okay, so when we look at negative 2y, if this is conservative, then that what? That's the partial with respect to x. So we take the partial with respect to y, and we get 0. And if this is conservative, this is a partial with respect to x to y. So we take the partial with respect to x, and we get 0. Conclusion? True, therefore, remember, if any one of these things is true, all the rest are true. It's a gradient field, right? And we know that, right? That's the one that was our gradient field, -2y. So here we're just confirming that that piece y equals qx. How about this one? Partial with respect to y of this one, 0. Partial with respect to this one, 1. Not equal. Confirming that we knew that what? Not conservative, not a gradient field. Does the Chloros Theorem thing make sense? So up till now, to find a potential function, we really didn't know. We started off the process. We didn't know if there was a potential function or not. We just tried, right? And if it worked out that we could get an f, then we said it's a gradient field, conservative. And if it didn't work out, then we said it's not. Well, now you can do there's a little check you can do first before you go through that process of trying to find f, little f. You can check using Chloros Theorem. And then if you get this case, then you don't have to go through the process because you know that there's not going to be a little f. Okay, next thing. We said this. The circulation integral for every closed loop in C, no matter any closed loop that you pick in a conservative vector field, the line integral will be 0. You have conservation of energy. Think of this as a work integral. You get conservation of energy. So back to 0 when you get back to your starting point. That's true for every closed loop. Okay, and the next thing we said was path independence. So the vector field is path independent. For any 2 points A and B and F, your line integral is constant for every path C from A to B. Change A or change B or change both, you're going to change the value of the integral. So in the past, students have been under the impression that every line integral has the same value. It's dependent on the starting and ending point that you choose. Okay, and then there's one more that we haven't gotten to yet. So, but we're going to talk a little bit more about these. Do a few more examples. Any questions on what we've got so far? Again, if any one of those things is true, then all the rest are true. These are all mathematically equivalent statements. Okay, so a couple little quiz problems here. These are all supposed to be ready for me to go. Where are they? Okay, so I want you to look at this vector field here. I've got this path, and I want you to discuss whether you think this is a conservative vector field or not. Is this a conservative vector field or not? And so you could have a discussion with, you think about it, and then talk it over. Conservative or not? Go. What would you guess? Okay, so a clockwise loop. Do you predict that that circulation integral will be positive, 0, or negative? Positive. About a third of you said positive.
For the entire loop?
The entire loop.
Yes, positive.
Positive. Positive?
Yes.
Let's check it out. So what about here at the beginning?
Near 0 to a little bit negative.
So we got negative, starts off negative over here, right? What about through here?
0.
Essentially 0, right? Essentially 0. It's angled a little bit, but these are essentially 0. Okay, then what about this side over here?
Really positive.
A lot of positive, right? It's kind of following the whole, strongly positive this whole way. What about through here?
Near
0.
0.
Conclusion?
Positive.
Positive? Conservative vector field? No, right? No. And let's check it with the Chloros Theorem thing. So this vector field is sine y1. Did someone guess that? Good job. All right. So what do we do to do Chloros Theorem? We look at this one. So we say if this were a conservative vector field, that would be a partial with respect to. No, it would be with respect to x. And so what do we do to it? Take the partial with respect to y, and we get cosine y. And if this were a gradient field, this would be a partial with respect to y. So we partial with respect to x is not equal, right? Confirming this is not conservative. Make sense? Okay, how about this one? So think about this one. So conservative vector field or not? Go. Sorry. There we go. Sorry. What do you think? Conservative vector field? Because? So it looks like that circulation integral is 0, right?
Yeah.
So is it a conservative vector field? Some are saying yes, some are saying no.
It's inconclusive because it's all 0 at all points.
Let's look at this one. Oops. Not what I wanted. Shoot. Try this again. Square. It didn't happen this morning. I'll just do this. How about that one? If you go someone said if you go clockwise, it's positive. Do you agree with that? Because over here, it's negative. But what about those vectors? Smaller magnitude, right? When we get over to the positive side, we have larger magnitude positive. So conservative vector field? No. Okay, so what's the point? In a conservative vector field, every circulation. So just because you show one circulation integral looks like 0, by no means proves that's conservative. Every single one has to be 0. Okay? So you can't really prove it by looking at 1 or 2 or 3 paths and saying, oh, these are all 0, therefore it's conservative, right? Because a proof would be checking every single one, which is impossible. So proving it, proving that a vector field is conservative, you're not going to go the route of, oh, I'm going to show that every closed loop is 0. Okay? By doing every closed loop, because that's too many, right? So let's check this one. Oh, so actually, this one is x squared xy. Okay, so show that confirm that that's not conservative, right? So this is, the vector field you're looking at is essentially x squared xy. So prove that it's not conservative. We found, all it takes is one loop that's not 0, and that proves non-conservative. But you need all loops to be 0 for it to prove it is conservative. Okay, so we'd end up comparing what? 0 with?
Y.
So we're going to do the partial with respect to x, which equals y. Okay, is this making sense? All right, so let's do something in 3D here. So last time we talked about how, what's an example of conservative vector field. So the force field that you're living in right now is a conservative vector field. And you know that everyone's force field is different? Why is everyone's force field different? My force field that I'm in is different than Seth's. It's different than... What's that?
Mass density distribution.
Yeah, so force, so in terms of the force of gravity on your body is your weight, right? That's so the force field that I live in is dependent on my weight, right? And same with yours. So let's take someone who... Wrong one. All right, we're going to take someone who's 75 kilograms. That's something between 150 and 200 pounds, right? Okay, so a 75 kilogram person hikes from negative 0.5, 0.5, 0.01 to 0.85, 0.865, 0.98 on this mountain. So here's negative 0.5, 0.5, 0.01. And then there's 0.85, 0.65, 0.98. And here is that mountain. Where's the mountain? That's up here. Okay, so there's the function for the mountain. It's a what? It's a multivariable real valued function, right? So it's a surface. So maybe this is Gandalf, right? Maybe this is Gandalf, and he needs to get to the top to save Frodo, who's about to hold on to the ring and not throw it in the fires of Mordor. All right, so here we go. Here goes Gandalf, and this is the way he's going to go. He's got his rock climbing equipment. He's going to go down there, and then he's going to make it to this ridge right here, and then he's going to go like this, and then down the ridge here. Can you see the path? So let's take the path somewhere where you can see it here. Okay, so here's Gandalf's path, and we want to find the work done by the gravity field to get from the blue dot to the red dot. And it's along this path, along this surface, through the gravity field. Can you do it? If you're smart, you can do it.
Yes, actually.
So let's first of all let me tell you what the gravity field is. So the gravity field would be then, or the force field, the force of gravity, Fg. That's going to be a three-dimensional field now. and what is that? 0, 0, and negative 9.8 times 75. So we can't do, and I think that's 735. And that's newtons. So negative, so the gravity's force field on Gandalf is 0, 0, negative 735 newtons. Okay, so we can't do the simple Chloros Theorem check. There is a three-dimensional check. We'll get to that later. So we can't do just the, what, Py equals Qx. But we can just see, I mean, is this a conservative vector field or not? Is it conservative? If it is, then there's some f, x, y, z, whose gradient field is 0, 0, negative 735. So is there a potential function whose partial with respect to x is 0, partial with respect to y is 0, and partial with respect to z is negative 735? What would it be? Negative 735z. Conclusion about this force field? Conservative. It's a gradient field. It's conservative. And now I got to find the work that force field's going to do as Gandalf makes this hike to the fires and mortar. Just throw the ring in there.
Yeah.
What's that?
Just go from point to point.
So how are we going to do this? Who thinks they know how to do this? So it's all about the fact that our force field is conservative. Therefore, if it's conservative, it's
Any path you take is going to be
path independent. So what path are you? So instead of calculating the work along this path, we know it's the same as the work along what path? Straight line. Maybe. There it is. So through the force field, so the work along that straight line path is going to be the same as the work on the path that he hikes through the mountains, because we have a conservative vector field, right? It's a gradient field, and so it's through path independence. What's that? No, because in both cases we're starting at the blue point and going to the red point. So is it going to be positive or negative, our result? So again, the path in the overall sense, is the path going against the forces or with the forces? Against. So we're expecting a negative result. So I want you to set up. You're going to find the path C. As a vector function, right? So you're going to make the vector function for the straight line segment from here to here. And so maybe the technique I showed you is going to be the easiest one. Do you remember that one? So starting at negative 0.5, negative 0.5, 0.01, to 0.85, 0.65, 0.98. We're going to write what that would be. So make this t equals 0 here, and make that t equals 1. So can you parameterize that segment from there to there, with t being 0 being the first point, t equals 1 being the last point? So work on it, check with each other, find the work that the force field does. Find the work that the force field does. What's that? No, that's because of the way that we made the parameterized. So this technique of parameterizing means that your starting point is 0. Because you plug 0 in, you get that starting point.
Yeah. So for C,
Oh yes, down here. Well, it's not C. Yeah.
that's where we chose our T value.
Yeah, I shouldn't have put C here. So I could do C when I do this, but once I get it into T, I'm not going to write C anymore. So the work is the line integral, and that's going to be from 0 to 1 of f dot dr. And our drs are 1.35, 1.15, 0.97. So when you do the dot product, you get negative 735 times 0.97 from 0 to 1. That antiderivative is just that thing t. Plug in 1 and 0, and we just get
Negative 712.95.
and that is, so if this was in meters, but this is not in meters, right? And maybe in kilometers, but so some, whatever, work units. So if it's kilometers, it'd be kilojoules. Yeah. So yeah, if this was if these were all in kilometers, these distances, then we'd have kilometers, newtons. Kilometers, newtons would be kilojoules. Okay, so just as a preview, so we found this integral, but we have something of an antiderivative of f, right? Because if f is a gradient field, right? If f is a gradient field, then it's like the derivative of what? No, not the surface. The potential function, right? So if it's a conservative vector field, it has a potential function such that this is like the derivative of that potential function. So there is a fundamental theorem of line integrals that says this won't take long. So if you have a gradient field, then if you have a conservative vector field, then that's the gradient of f, right? And the gradient of f is essentially the derivative of f, of little f, right? It's essentially a derivative of your surface. But it's not a surface. We're in 3D now, okay? So little f is not the gold surface. What is little f? Little f is the potential function for our force field, which is what? What was it? What did we say it was? Negative 735 z. So that's not the gold surface. Don't get confused here. So we're in R3. So the potential function is a function of 3 variables, not the gold hill. Okay, they're totally different. So this is our potential function for the force field, and this vector field is essentially that is its gradient. So it's its derivative. So what does the fundamental theorem say? It says that we can take the net change of our antiderivative, or the net change of our potential function. So we can do f of b minus f of a. So it's just like the fundamental theorem from Calc 1, right? So what is f at point B? Negative 735 times the z coordinate at 0.98, right? Minus negative 735 of the potential function evaluated at point A. Or, sorry, minus the potential function evaluated at point A would be negative 735 times 0.01. Exact same thing. So we did it. We did this. We did the line integral way, and we got a certain amount of work. But since we have a gradient field, we have an antiderivative, or we have the potential function, right? Whose derivative is that gradient field. So we can just do the net change of the potential function from final minus initial, right? So it's the net change of the potential function. Final point, final value of the potential function minus initial value of the potential function is the net change, and it's the same. So that's the last. That's the last thing. We'll prove it next week. We'll actually or show kind of where this comes from, but it's totally parallel to your fundamental theorem from Calc 1. So just to go back here. Last bullet point is that the fundamental